we're going to look at some examples here where energy is not conserved. We're still using the same equation. Work non-conservative is delta KE plus delta PE. But now this work done by non-conservative forces is not going to be 0. Let's say that a catapult throws a rock with mass 19 kilograms at a speed of 22 meters per second at 38 degrees above the horizontal from 2.5 meters above the ground. When it hits the ground, its speed is 22.5 meters per second. How much work is done by air resistance? So this question is identifying air resistance is a non-conservative force that is acting in this problem. So for the work non-conservative, we plug in work done by air resistance, and then we have delta KE, which is 1/2 m. V final squared is 22.5 squared minus V naught, which is 22 meters per second, 22 squared. That's 1/2 m V final squared minus V naught squared, plus delta PE. In this case, we only have gravitational potential energy, so that's m, which is 19, times g, 9.8, times delta h, which would be height final, which is 0, minus height initial, which is 2.5. And we can punch that into the calculator. 0.5 times 19 times 22.5 squared minus 22 squared, plus 19 times 9.8 times minus 2.5. And we get that the work done by air resistance is about minus 254.125. Well, not about, exactly. Minus 254.125 joules. It's important when you're doing these problems to think about your answer for a second. If you got a positive number for work done by air resistance or friction, that would be a problem, because frictional force and air resistance always exert a force opposite the direction of motion, so they should always do negative work. So that's just one thing to keep in mind when you're solving problems. Work done by air resistance is going to be less than 0. Work done by friction is going to be less than 0. So if you get a positive answer, then there's something wrong. Either the problem statement could potentially be inaccurate, or if it's something that I just make up on the spot, or if it's a question in the book or on a test, then you've probably done something wrong. It is also worth noting, what was it worth noting? I remember. It was also worth noting that this angle didn't wind up coming into play, and it turned, the energy change is not dependent on what this angle is. So this angle will affect things like how far away the rock is when it lands, and what the angle of its velocity, which are things that we saw when we were doing kinematics, but it doesn't actually affect the energy change, so it doesn't affect the final speed when the rock hits the ground. Another example, we have a block with mass 2.3 kilograms. It starts from rest on a plane inclined at 34 degrees above the horizontal. The question is, when it has traveled 1.3 meters along the plane, friction is done, minus 5.9 joules of work. What is the block's speed? We can just plug that in. Work non-conservative is minus 5.9. Our change in kinetic energy, 1/2 m, which is 2.3. V final squared minus 1/2 m V naught squared. V naught is 0 because it starts from rest, plus m g. Our delta y is negative again, 1.3 sine 34. And we can rearrange that and solve. That gives us minus 5.9 plus 2.3 times 9.8 times minus 1.3 sine 34. Times 2 divided by 2.3, square root. What did I do? Minus 5.9 plus 2.3 times 9.8 times 1.3 sine 34. There we go, is 10. I don't know what I did before. Times 2 divided by 2.3. Square root, we get a V final is 3.0195, etc. meters per second. Alright, let's go ahead and do an example that involves a spring. Let's say we have a block with mass 2.3 kilograms is pressed into a spring with constant 17 newtons per meter, so that the spring is compressed 12 centimeters from equilibrium. Then the block is released, and its speed when it reaches equilibrium is 23 centimeters per second. How much work is done by friction? All right. So I should have mentioned this is a horizontal spring. So this is what I'm picturing. We've got a block on a spring, and it's resting on the surface of something or other. All right. So the work done by non-conservative forces, in this case, our non-conservative force is friction, is equal to half mv final squared, 23 centimeters per second, so that's 0.23 squared, minus, well, it's pressed into and then let go, so its initial velocity is 0. And then in this case, we have the spring force plus half k delta x squared. The spring potential energy, half 17, and it's compressed 12 centimeters from equilibrium, 0.12 squared. So then that is the work. So when we add the spring potential energy, it should be 1/2 k x final squared minus half k x naught squared. Right? And our x final squared is 0, our x naught squared is 0.12, so there should be minus half times 17 times 0.12. So if we punch that in, we get that our work done by friction is minus 0.61565 joules. Now, there are 1,000,001 problems I could come up with to do conservation of energy or non-conservation of energy applying the work energy theorem. Those are a few examples that should help you get a jump on the rest of them.